Okay, now we'll have Marisha read problem number 3, which I asked you to try on page 147.
Show that if Abel plays 1/2 R1, 1/2 R2, Baker can do better than 3 seconds by playing C3.
Okay. Unfortunately, I'm sorry, I always forget when I assign this problem that it has a terrible typo in it. The problem as stated is not solvable, okay? But remember, I want to point out something using this particular problem. I apologize for assigning it, but you'll see on the solution key, I'll show you what you can do with this particular problem. I want you to notice something here, though. So what I've done is, just like I did last time, I've written out the expected value if they're playing a coordinated strategy, where on heads, they both choose going skiing. On tails, they both choose going to the festival, ruling out these other 2 payoffs, and we saw that that has an expected value of both of 3/2. If, on the other hand, they just play the heads-tails strategy independently of each other, we saw that that has an expected payoff of only 1/2. So if they can coordinate their strategies into a single coin flip rather than both flipping a coin individually, they will increase the value of the game from 1/2 to 3/2. But notice the following. This is where it gets really interesting. Suppose Column or Baker knows, because he knows Abel or Roe, that Roe is actually going to do this. Is actually going to flip a coin, but he can't communicate anymore. Is actually going to flip a coin and is going to play this strategy, 1/2 R1, 1/2 R2. Notice, however, that if that's the case, that Baker can increase his or her value of the game by simply shifting and playing C2 with a probability of 1, going to the festival. Because now calculate the value of this game for Column or for Baker. Knowing that Roe's going to flip the coin on his or her own, half the time Roe's going to wind up playing R1. So if Column goes to the festival only, that will be 1/2 times 0. And half the time Roe's going to go to the festival, 2 times 1/2 equals 1. By playing the pure strategy of going to the festival, knowing that Roe is going to flip the coin, Column will have an expected value of 1, not of 1/2. So by saying, sure, let's flip the coin, we'll independently flip the coins on our own. If Column then knows Roe's going to flip the coin, Column will automatically choose going to the festival to raise his or her expected value from 1/2 to 1. But Roe knows exactly the same thing. Roe knows that if Column is going to flip the coin, Roe would do better, could increase his expected value, her expected value, from 1/2 to 1 by simply going skiing alone. And so after they've decided we'll just flip the coins on our own, so we'll each have a value of 1/2, now both has reason to switch off that expected value, play their dominant strategy, R1, C2, and look where they're back at. A payoff that is less than if they both would have independently coordinated their strategy. Isn't that fascinating? So by cheating, the other will be tempted to cheat just as much, and now they're back at a payoff that's disadvantageous. A payoff of 0/0 as opposed to a payoff of 1/2 if they both would have stuck to their agreement to independently flip the coin. Fascinating. Selfishness killed them. But selfishness motivates them to switch off that half-half strategy to their pure strategy, but it motivates the other to do it as well, and now they're back on that non-optimal equilibrium point with a lower expected value than if both would have stuck to their deal and flipped the coin. Ain't this game theory fascinating?